Hey guys, Mr. Canister here. In today's video, we're going to talk about springs and things. We're going to use Hooke's law to figure out what the spring constant in a spring is, aka what is the spring stiffness of a spring. And we're going to figure that out using a graph of force versus stretch for a spring. We're also going to figure out how to find the total work done when you're pulling a spring, aka when you're stretching it, again, from examining a graph of force versus stretch. So before we do that, let's go ahead and open up an applet and just simply consider a spring. So what are the things you can change about a spring? If I were to, for example, hang a mass from a spring, you see that it stretches by some amount. And so the basic premise is by hanging weights, aka by applying a force, because forces are what we talk about as far as pushes and pulls in physics, on a spring, you cause it to stretch. Let's see if we can figure out any relationship between how much force we put on a spring and how much it stretches. So on the bottom, all these weights are listed as 50 grams, 100 grams, 250 grams. That's the mass. The force pulling on the spring is the mass of this weight of this object times the acceleration due to gravity. So first, by putting the 50-gram mass down there, it looks like it causes a stretch of about 5 centimeters, give or take. If we look at the difference from the line from where it goes to where it ends, looks like it's about a 5 centimeter stretch. Now, if we look at the 100-gram mass, it looks like that causes about a 10 centimeter stretch. So it looks like double the mass, aka double the force, causes a double stretch. Let's try it again. 250 grams, go ahead and make a prediction what you think it should be. Go ahead and make that prediction right now. And when we hang it, we see about a 25 centimeter stretch. So it looks like there's some kind of a direct relationship between the force applied and stretch. When we actually examine it, we see the following. If you graph the force on the y-axis and the elongation or stretch on the x-axis, you see in fact that it is a direct relationship, aka if I were to go from a 2-meter to a 4-meter stretch, it would require going from about a 5 Newton to about a 10 Newton force, aka to double the stretch, I would have to double the force, or if I double the force, I double the stretch. What we're going to do though is examine the concepts of slope and area and use those to figure out spring stiffness and energy stored in the spring, aka the work done to stretch a spring. So for the next segment, consider the following. Consider 3 possible graphs for different springs. So for example, consider the 3 different springs that are on this page. Maybe the first spring produces the graph as shown. A second spring produces a graph like this. And a third spring produces a graph like this. What would be the big differences between those? If you look at it, the third spring, well, it takes an awful lot of force to produce just a tiny bit of stretch. But the second spring, it only takes a tiny bit of force, looks like about 7 newtons, to produce a humongous stretch. So for the third spring, we would say this is a very stiff spring. And for the spring on the bottom, we'd say maybe this is a soft spring, something that's not very stiff at all. What we're going to do is the spring stiffness, aka how stretchy it is, we're going to define that as the spring constant. And the spring constant, we're going to give the letter K for spring constant. We want to figure out how can we solve for the spring constant of a spring. Well, just from looking at the graph, we reasonably deduced that it looked like kind of the steepness of the graph, aka the steeper I made my graph, that made a stiffer spring. So the spring constant really has to do with the steepness or the slope of the graph. And if you remember slope as being the rise of a graph divided by the run, we see that the rise of this graph is the force applied, and the run of this graph is how much the spring stretches. So the slope, the rise of the run, is really the force divided by the stretch. Written as letters, we use the letter F for force, and we're going to use the letter X for stretch. And so solving, we get the following. The spring constant of a Hooke's law of a regular spring is the force it takes to stretch it divided by the stretch. Or written in terms of force, the force acting on a spring, we just use a little subscript S for force for spring, equals the spring constant times the stretch. And there is Hooke's law. This equation is used most often when you're given a force and a stretch to solve for a spring constant, or if you're given the properties of the spring, its spring constant and how much it stretches, you can figure out how much force it took to do that stretch. Awesome. So that's the spring constant of a spring. What we're now going to do is examine how much work did it take in order to stretch a spring. So what we're going to do is I'm just going to erase a little bit of this, clear the space. And our goal now is to examine how much work did it take to stretch the spring, maybe to that distance. So recall from the previous videos that the work done on an object is equal to the area of a force versus displacement graph. And notice when you stretch a spring on the y-axis we have a graph of force, and on the x-axis we have a graph of elongation or stretch, which is a displacement. And so by taking this area we're going to get the work done. So let's find that area. So this area is the area of a triangle, and so the area is the work done on the spring, and that's the area of a triangle, which is 1/2 the base, which is stretch, and the height, which is the force acting on a spring. Well, just not even a minute ago, we learned that the force acting on a spring from Hooke's law is equal to kx, the spring constant, times the stretch. So what we're going to do is we're going to plug in, since these two terms are equal, plug in our kx into that force as a substitution. Simplifying and solving, we find that the work done on a spring is equal to 1/2 the spring constant times the stretch squared. And there is the formula for the work done in order to stretch a spring, aka if you know how stiff your spring is and how much you've stretched it, you can calculate how much work you had to do to stretch or compress it. Awesome. In the next video, we're going to then use this work to calculate how much energy is stored in a spring, and from that we can then use conservation of energy to figure out lots of neat things about how toys and lots of elastic materials work. All right, hope that helped. Have a great day, everybody.